Hey, hey, did you miss me? Good morning, everyone. Let's go to some exercise chapter 4. And I'm picking here and there from your book. So basically, in chapter 4, we introduce Newton's law. And there are three of these laws that you have to know. You don't need to know more than that. The first one is the law of inertia. And what is the key aspect of this law? If something is at rest, right? So you have oops, you have, and I think that was an example that I like to give always. You put a book on a table, the book will stay there. It's not going to move unless somebody forces the book into motion. So the law says if something is at rest, it will remain at rest. Or if something moves, now you have the book moving with a velocity that is constant. If the velocity is constant, and this can only happen because the net force on the book is zero. So if you have something pushing the book and something resisting the motion of the book like friction, the sum of these two actions is zero, is none. The book will keep on moving with the same velocity forever and ever and ever and ever. Okay, so that's a consequence of Newton's first law. Now, the Newton's second law states that if the net force on the book is zero, so it's not zero anymore, then the net is such that force is equal ma. M is the mass of that object. Acceleration is the change of velocity over time. So by now, when you hit chapter 4, you should have some understanding about the differences between acceleration, velocity, and displacement, right? So that's key for you. And acceleration is related to a net force. The direction of this net force matched the direction of acceleration. Okay. So let's see how this unfolds in this exercise. In a collision between a big SUV and a small car, the SUV exerts a larger force on the hybrid than the hybrid exerts on this SUV. Is this true or false? Oh, the answer is there, but that's not fun. So what's going on? So you have a big thing that is moving, let's say, to the side and collides with a little thing that is either moving to the right side but not with the same speed, or is going towards it. It doesn't matter. When the collision takes place, and according to, oh, I forgot the third law. The third law of Newton states that every action implies a reaction, same intensity, which means the number associated with the force. The number is the same, but the direction is opposite. Is the law of action reaction. So you pull against the wall exert a reaction against you, same intensity but opposite direction. So this exercise is an example of Newton's third law. So the big SUV exert a force on the little block to the right as it collides. According to Newton's third law, the little block exerts a reactive force to the left on the truck, same intensity, which means the size of this vector is the same, but opposite direction. Which you might think doesn't make sense, but according to Newton's third law, this makes total sense. If you punch the wall punch against you, same intensity, opposite direction. When Earth is a big thing, right? It's a big planet. So Earth pulls you down with a force with the same intensity in which you pulls Earth upward but the direction is opposite. Okay. So this is false because the intensity of the forces are the same, but the direction is not. Box is placed on a table which rests on the table. The box pushes on the table. So let's see the situation. A box is placed on the table which rests on the floor. Oh, that's the table, and here's the floor. Okay. The box pushes on the table. The reaction force of the box pushes on the table. So let's represent this force here. So you place the box, let's say throw the box on the table, and the box exerts on the table. This is force box on table to the side. The reaction force to the box push on the table is the table push on the floor. So the table on the floor is some weird thing. No. So the table will react to this action with a force that has the same magnitude but opposite direction. So the representation that I make here is a representation of force table on the box. So in the lab, when we did exercise of a free body diagram, when you do a free body diagram, let's say the free body diagram of the box on the table, you have to ask which forces are acting on the box. You don't care what the box does on everything else in the universe. You care for the forces the universe does on the box. And that's why in this example, if you throw a box on the table, right, the moment the box gets in contact with the table, what are the forces on it? So let me represent here. The forces are force of gravity, which we studied before, the normal reaction table, on box, and also the force the table exerts on the box. Table on the box or on the book, okay? Which is friction. In chapter 5, we will call this force here friction. So those are the forces acting on the box once you throw the box on the table. And because of this resistant force, when you throw something on something else, you throw, let's say, your shoes on the floor, the shoes don't keep moving forever. They stop because of frictional forces. While flying horizontally in an airplane, you notice that a string dangling from the overhead luggage compartment hangs. Okay, so you are sitting there, and then this is the overhead compartment, and you have something that is 15 degrees away from the vertical towards the front of the airplane. So you're sitting here. That's the front of the airplane. Change the color. This is the front of the airplane, and you have something dangling 15 degrees towards the front of the plane. So if this is the front of the plane, certainly the plane is moving that direction, right? So the airplane doesn't move backwards. Never saw that. Probably a helicopter can do that, can it? So using this observation, you can conclude that the airplane is what? Well, look at this. What are the forces? I have always to ask this. What are the forces? What are the forces on this mass? So I like to represent forces by red marker. So the forces are, you have the gravity force, and you have a string force. Those are the two forces only. So the airplane is moving in that direction. But the force of tension, see, there is a string, there is tension, and the force of gravity are those only one. So if you take the direction of motion, right here, and right there. Call this your x-axis and your y-axis. The direction of motion, positive x direction is given. That's the direction of motion, right? So what are the forces projected along the direction of motion? Well, gravity does not project along x-axis. The projection of gravity in the x-axis is none. But the tension force does. See that? So the tension force projects a component to the left. The tension also projects a component, which is the rise, in the positive y direction. This is your ty, this is your tx. So the tx component, the tension component projected in the x direction, is projected along the negative direction. So is there an acceleration going on? And the answer, yes, there is. The acceleration, according to Newton's second law, is given right here, is directly proportional to the projection of the tension force in the x-axis, which is to the left-hand side. And then you get a situation we studied in chapter 2. The velocity is to the right. The velocity is to the right. The acceleration is to the left. Both vectors have opposite direction. So you have a situation of decelerating process. So it's all it's slowing down. So you have a slowing down, your airplane is slowing down basically. So it's moving forward, this is correcting, and accelerating backward. Well, the airplane is moving forward. This is correct. It's fun. Should be D and A. Flying horizontally in an airplane. Yeah, the airplane is moving forward. This is correct. And is accelerating backwards. So you don't trust all the solutions in a book. An elevator suspended by a vertical cable is moving downward. That's the cable. That's your elevator. The elevator moves downward. So if you take your y-axis like this, your x-axis like that, the elevator is moving in the negative y-axis direction. But is slowing down. So this is the direction of your velocity vector. If it is slowing down, acceleration must have an opposite vector. So it should be pointing upward, which means the net force in the vertical direction, has the same orientation as that of your acceleration. That is the net force. Okay, so that's the net force. Now you go to the exercise of identifying which forces acting on the elevator. So here is your gravity force, and you have a tension force, like that. So what is the net of these two forces? The net of these two forces is the subtraction, or the difference between gravity and tension. The difference between gravity and tension. So which means if the positive direction is in the y-axis, so T minus Fg, T positive pointing up minus Fg pointing down is equal M AY, and the acceleration in y is positive. So which means this quantity is a positive number. So your tension is bigger than the acceleration, the elevator weight, which is Fg. So A is the right answer, since the tension is bigger than the weight. A crate is sliding down an inclined plane. Oh, let's make an inclined plane here. It's the crate is sliding down an inclined plane at a constant speed. So we have a constant speed of some number per second. The vector sum of all forces acting on this crate must point what? Is 0. Vector sum is 0. The speed is constant. If the speed is constant, so you have a straight line, the acceleration is 0. If the acceleration is 0, the net force is 0. So what is the net force on this crate? Let's just outline the forces just for practice. You do have your gravity force, and you have your normal force, and you necessarily must have friction force. Why? Because when you study the motion along this direction here, x direction, see I'm tilting the x and y axis, and y, I'm putting a different color, that's your y-axis. By the way, are you guys going to the tutoring center? I didn't receive any request to help in anything so far. I only heard Professor Walton saying that you guys or somebody approached him saying that was too difficult, but I haven't received any requests, and I talked to my tutor students and they haven't received a lot of requests either. So again, you guys have to study it. Without that extra effort, you guys can't do much progress, at least some of you. So in x direction, what are the forces in it? Friction and the projection of gravity along that direction. Here it goes, Fg, and I'm calling Fgx right there. Your Fgy is right here, Fg in the y direction, okay? So the net of these two forces, friction and Fgx, must be equal 0. So yeah, there is no option. Now they did it right. An object of mass m rests on a flat table. Go. The Earth pulls on this object with a force of magnitude mg. There you go, mg. What is the reaction force to this pull? The reaction force to this pull, some of you might say, is the normal force, but it's not. The normal force is the force the table, the floor, exert on the book. The reaction force of Earth on the object, which is mg, is the force the object does on Earth. Here's the planet Earth, this is the object over there. So as the Earth pulls this object down with the force mg, this object, believe it or not, exert a pull on Earth that has the same magnitude but opposite direction. So you sitting on the desk or the table watching this video is in fact pulling Earth upward towards your butt as you sit on the chair. And because of that, you are sitting on the table complains and then exert a normal force on you. But the pair action reaction is Earth on you and you on Earth. And when we do free body diagram on you, we ask which forces are acting on you. Forces acting on you are Earth and the normal force. Okay? A person who normally weighs 700 newtons rides in an elevator that is moving upward but is slowing down at a steady rate. So let's illustrate the situation. I will certainly put some elevator situation exam next time. So you have an elevator. So you are sitting right there in an elevator. The elevator is moving upward. That's the direction of motion, which happens to be the positive direction. We all, by convention, call upward positive. But it's slowing down. If it's slowing down, it means there is a downward acceleration. Since velocity is in the direction of motion, always velocity is in the direction of motion, is the direction of the displacement vector. And if it's slowing down, the acceleration must have an opposite direction. So you look at this head here, these two heads must oppose. So if you are talking about a deceleration. So if that is the case, there is an imbalance of forces on you, and that means, or in the elevator, you do have a tension force, and you do have a weight pulling down. So since acceleration is downward, it means these two forces are such that mg is bigger than tension. Mg is bigger than tension. Since mg is negative, tension is positive, your acceleration must have a negative number. That's how you would set the equations if you want to solve this problem. Again, I might be going fast here, but if I am, you have to ask, or you have to go to the tutoring center. But it's slowing down at a steady rate. If this person is standing on a bathroom scale inside the elevator, what would the scale read? Well, now let's put you sitting on a scale. So here's the scale. That's the scale. So if this is the case, what are the forces on you? The force Earth exerts on you, Fg, and the normal force the scale exerts on you, right? So the net of these two forces is downward, right? So this person is standing in the bathroom elevator like this. That's the scale. Moving upward, but it's slowing down. So again, direction of motion, and it's such that the velocity you have with respect to Earth is positive because you're moving upward, but the acceleration on your body is downward, which means Fg is bigger than the normal reaction. Wait a second. So if you do, just erase this for a second. It's a big wind outside. Can you hear? It's amazing wind. So when you do the laws of motion, so the motion is upward is the positive. You have Fn minus Fg is equal ma. Okay. Wait a second. Is equal ma. But what is the direction of your acceleration vector? Is downward. So your acceleration vector will have a negative sign. So it's a number, let's say 1 meter per square second or 2 meters per square second, but it has a negative sign because the acceleration itself is downward. Like when you place g in your equations, you place g with a negative sign. So what is the scale reading? The scale is reading your normal force. So your normal force will be mg. So when you add both sides of the equations by mg is equal mg plus m negative a. In other words, your normal force is mg minus ma. So the normal reaction force, which is the reading of your scale, is going to be less than the weight. So there you go, B. So I have this, I'm going to put this handout online on Canvas, and then you guys try to work on it. If you can't work on it, let me know. Ask questions, okay? And don't let to resolve these problems 2-3 days before the exam and email me saying, oh, well, I'm all struggling. You will struggle if you try to work hard the last 2 days. It doesn't work. You have to do every day a little bit, and you cannot be behind. You cannot be studying now chapter 2, okay? So let me do number 7 as the last one, and if you need more, I can do later. But you have to ask again. Block is on a frictionless table on Earth. The block accelerates this much when a 20 newtons horizontal force is applied to it. Block, we have a force, 20 newtons, and there is an acceleration, 3 meters per square second. So see, all of this is such that I'm calling to the right a positive direction. The block and the table are set up on the moon where the acceleration due to the gravity is less. The weight of the block on the moon is close to, well, that's a simple one. It doesn't matter what acceleration is going on here. Oh, wait a second. Oh, I know it. So on Earth, a block on a frictionless, okay. So the block acceleration is given, the force is given. So what are the forces on this block on Earth? You have the weight of the block, which is mg. You have the normal reaction to that of the table on the book, and you have this external force given by 20 newtons. According to Newton's second law, F is equal ma. So 20 newtons is equal mass times acceleration, which means the mass of the block is 20 over 3 kilograms. So we have the mass. So the weight of the block on the moon is given by its mass times the acceleration of gravity in the moon. So you have the mass of the block and you have the acceleration which is given. And then you have the value of the force in newtons. I don't know which one it's going to be. I don't have a calculator here. But then you can calculate the weight on the moon given by that. So the mass is the same, but not the weight. And what you solve, you apply Newton's law on Earth, and by doing that, you determine the mass of the block, and then you apply the mass is the same here or on the moon, and or in any other place in a Newton star, and then you can find the solution. See another one there, just to say goodbye. A catcher stops. So you have a ball that is traveling to the right with a speed of 40 meters per second, and it has, this is the speed, and has a mass of 1.5 kilograms. That's the m. And so the catcher, put a glove here, catch the ball, right? And it moves for 20 centimeters. See, I'm converting that to meters up to when the ball stops. So technically the ball travels this much, 20 centimeters, at the hand of the catcher, right? So the catcher kind of slow down a little bit, so it doesn't stop instantaneously. What is the magnitude of the average force that the ball exerts against his glove? Is, in fact, is equal to the same average force the catcher exerts on the ball, but it's given to what? Well, that force, the ball on the catcher is equal to the mass of the ball times its acceleration, right? And the mass is given. So we have to find the acceleration. So how do we find the acceleration? Well, we have the distance this ball moved, and we have its initial speed, and we know the ball stops. So the final speed, when the ball stops here, when the ball stops, the final speed is 0 meters per second. V final. So here's your V initial. So what do? You apply Bernoulli's to determine acceleration. How do you do that? V final square, V initial square, plus 2a del x. So del x is the block moves 20 centimeters, and then you can figure your acceleration is negative of final is 0, no, wait a second, the final is 0, this is 0, but the initial is 40 meters per second, right? Yeah, so this is 40 meters per second, and then you're going to have an acceleration that is 40 square meters per second. Yeah, 40 squared divided by 2 times 0.2. Okay, so it's a negative number because it's decelerating. So you take this number and plug it in here, and then you have the value of the force. Work on this problem. Let me know how that goes.